Now, I promised at the beginning to give you some talk about the quantum, the logical quantum interpretation, the first logical interpretation of the quantum behavior. I don't have enough time now to do that, but very quickly let's go. Actually, there are many theories already who have tried successfully to obtain the quantum behavior based on a fractal spacetime. But this fractal spacetime is not really correct, because how can you make spacetime fractal when you have different space and time and space are different? It becomes genuinely fractal only when space and time have the same unit. So here, because our time is time, our space is time, it's complex time, it becomes genuinely fractal, and therefore using the same theories already present, we can now use their already different methods to get the different quantum mechanical behavior. But here we go even further, because if you follow this more, you will understand why you are getting supersymmetry, as we already explained before. But now let me skip this because we talked about it already. Let me move further. Let me only mention this important point because it's one of the main ideas in quantum mechanics, which is the uncertainty principle. Now we know already that for example, the higher momentum you get, the less certain will be about position, and the smaller dimension you get, the less certain will be about momentum. But we don't know why. The reason why is because the object is made of many monads, let's say n number of monads, and it's being recreated from 0 to c at every sequentially, and therefore at any real point of time only one monad exists at c, while the others have already collapsed, because remember we have single, so only one at c and the rest will be at 0, but at 0 after they made their contribution. So in the end the momentum will be given by this equation. Therefore, because we have one monad at c, the position of this monad will be uncertain completely, because you know if you are moving at c, the uncertainty will be infinite. So we have only one infinite uncertainty, while all the rest of points have been already defined, and therefore the uncertainty will be proportional to the number of n. If the number of n is very high, only one, for example, in a million is undefined, then the uncertainty will be very small. And this is correct for large objects, or for example, objects moving or not moving. However, for very small objects, which are composed of smaller number of n, the uncertainty will be very small, will be very high, and also we will get high uncertainty when the object becomes move faster, because if the object move faster, it means that on average more and more points will be on the speed of light, and this will be on c, and therefore the total velocity will be higher, and therefore the momentum will be higher, and therefore the uncertainty also will be higher. So here we have a new equation that can give us an estimate of the value of the uncertainty based on the particle itself, how big it is it composed of small number of monads, is it moving faster or less or slower. All this is now a new idea of uncertainty. The same can be also said about the collapse of wave function. So actually, automatically the points are collapsing to 0, except the real current one. So the final collapse happens at the moment of measurement, and therefore only we know the total state at the moment of measurement. However, let me add here that for small systems such as a small number of particles, and because the observer is always part of the system, then the uncertainty will be related, the collapse of the wave function will be related to the observer, because the observer is itself a monad, or contributing to the system, because it's doing the measurement, and therefore the very observation can affect the measurement, especially for small systems, and therefore, for example, in the case of Schrödinger cat, the cat can be dead or alive. The state of the cat is already defined before we open the box, but we only know after that, just like now in the classical Copenhagen interpretation. But the only addition here is that the effect of the observer, for example, if one is watching his own cat and he is tied to it with like the same as entanglement, is entangled to the state of the cat, he can change the state of the cat before he can, for example, delay the spilling of the toxic material, and he can affect the experiment, and therefore the result will be related to it, especially when we have entanglement. And here, of course, this is a very big area where we have parapsychological effects that I really cannot speak about now. And I want now to conclude. Maybe I have already mentioned non-locality before, but let me again, since we are here, this is, I think, our final slide, that with this new ideas of entanglement and our understanding of entanglement and non-locality, the interaction between the different points can be close to instantaneous. Actually, it cannot be instantaneous, but can be very close to instantaneous, irrespective of the distance between them. Yet it's not even for example, suppose two particles at different points, different edges of the universe, they can interact in a very short time, much shorter than a normal travel, even if you are traveling at the speed of light, and that's because of the recreation. So we have non-locality explained without breaking the speed of light. Remember, because the speed of light is the speed of the creation itself, while the motion is in the outer time, and therefore they are orthogonal to each other and they don't affect each other. And I think here, finally, this is the final slide. With this new system, we can now easily understand the cause of causality, or the reason of causality. This is very simple. It will take only 1 minute, I promise. And this is because the universe, since it's self-contained space now, it's not contained in space, it's physical vacuum, and therefore it's self-contained. Therefore, it's a closed system. And therefore, any change on any part of this closed system will cause subsequent change in other parts, and therefore you will have subsequent causes. So any change in any part of the universe will cause corresponding synchronizing change. However, the new thing here is that this change can be non-local, can be even non-temporal, it can be changed in the future, maybe long future, and even can be retrospective, because you have now 2 arrows of time. But I think this point is not easy to explain, so I will skip it and then I will finish. And I thank you all for watching this long presentation, and I will put for you, as I promised, these slides and the paper or the book you can download from my website. I will put for you the link. Thank you very much.